Hey guys, it's Eddie the Magic Monk. I'm doing a live tutorial right now, I guess, because most people have just finished their exams here in Australia. I'm guessing there won't be many people here today, which is totally fine with me. Just gonna make a few tutorials, and if people are here, feel free to ask some questions. Otherwise, I'm just going to keep going with tutorials. Okay, so I guess I want to start talking about probability. And yeah, probability, we're going to probably focus more on stuff that is taught in Maths B, so senior maths. So yeah, most likely taught in year 12 perhaps. Yeah, it depends on which school you're studying at, I'm guessing. So I guess what we want to start off with is talk about what are variables. Okay, and let's call it discrete, random variable. Discrete random variables. Oh. So a variable, you guys all know what that is, right? But a random variable is when you can't really predict what's going to come up, right? That's why it's called a random variable, right? There is no way for sure for you to know, for example, if you conduct an experiment where you're shooting the basketball, there is no way for you to know whether how many shots you're going to get in your experiment. Right? You're going to take 10 shots. You don't know how many you're going to get in, do you? Hey James, how are you going? Raining outside, so you guys might hear a little bit of rain, unfortunately. It's probably a good thing anyway. So yeah, a variable can basically take on some sort of number. Okay, so for example, in an experiment, actually I should probably talk about discrete. So variable means it's a container for a number, right? It's like X, right? You don't know what is in X. There could be a series of numbers that you could put in there. Now, discrete basically means that you need to be able to count the numbers. Okay, so for example, the number of times you get a tail when you toss a coin, or the number of times that you roll a 6 when you're playing some sort of dice game. Right, that's why it's called discrete. Okay, so variable x usually. Okay, variable x, and we're going to put whatever number we want in there, and it has to be discrete and it's random. So you might be thinking, what is this guy on about? So let's come up with some let's come up with some examples. Okay, so let x represent number of heads obtained in let's say 4 tosses, 4 coin tosses. Okay, so you can draw up a little table. You can draw up a little table and you can go X can be, you can have no heads, you can have 1 head, 2 heads, 3 heads, or 4 heads, can't you? Now, you can probably list all the possibilities out. It might take you a while, but you can. And you probably do that in the form of a tree diagram. So, it's getting a bit hot tonight. Turn the lights off. The light's making me hot. Okay, so we have a probability of getting, actually let's just draw a tree diagram first. Okay, so let's just go first toss. You can either get a head or a tail. Alright, that's from your first toss. And then let's say you do it again. Second toss. Getting sore shoulders. Went to the gym today. So yeah, you can either get a head or a tail again, so that's your second toss. And then there's your third toss. You get head or tail, head, tail, head, tail, head, tail. And then each toss after that, you're going to go head, tail again. It's sort of hard to write out all this space because there's not enough space there. But so yeah, you have 4 heads in a row, so you just go, so this is your outcome. So you got 4 heads, you go head, 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 tail, head, head, tail, head, 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 tail, tail. Oh, getting tired writing this out. Mr. Panda. I'm great, Panda. How are you? Getting warm these days, hey. Summer's coming soon. Or actually not summer, spring. So yeah, head, head, tail, tail. And then what do I have? Head, tail, head, head. Head, tail, head, tail. Head, tail, tail, head. Head, tail, tail, tail. Ooh, getting tired writing this out. If there was someone else here, I'd get them to write it out for me. So yeah, let's go tail, head, head, head. Tail, head, head, tail. Wait, these line up. Tail, head, tail, tail, head, head, tail, tail, tail. Tail, head, head, head. Tail, head, head, tail. Head, tail, head, tail, head. Tail, head, tail, tail. By the way, you guys are probably thinking, I hope it's not going to be this hard, but there is going to be a shorter way of doing this, doing what we want to do, so don't worry, I will teach you the shorter way. Eventually, tail, tail, head, head. Tail, tail, head, tail. Tail, 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 head. And tail, 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 tail. Finally. Okay, so what we're going to do now to fill out this probability table. Okay, what we're going to do is we're going to go we're going to write in the table, we're going to write the probability of getting the probability of x being equal to the number above. So x is capital here and x is small case there. So for example, what is the probability of x being 0? And we're going to write the answer here. Probability of x being 1, and we're going to write the answer here, and so on. Alright, what are we going to be learning? Well, we're just doing a little bit of probability today. So, Panda, where are you based again? I mean, do you know much about probability? So, what is the probability of getting 0 heads? Well, you can see here that each of these outcomes have an equally likely chance of occurring. Okay, because there's a 50% chance of this tree going either up or down, isn't it? 50% chance, 0.5 chance. That could go this way or it could go this way. And then once it has gone this way, let's say we've tossed one head, then the next toss, it has an equal chance of going that way or that way. So every single layer, I guess you can say, has an equivalent, every single path has an equivalent chance of occurring. Might just type it out for Panda here. We're learning probability today. Not sure if he's gonna care about it. So every single path has an equivalent chance of occurring. So therefore, all we're going to do is count how many outcomes are here. Okay, so let's do a simple count. We got 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes, and then, well, they're basically 2 trees, aren't they? So if there's 8 outcomes at the top, there's going to be 8 outcomes at the bottom. So it's 16 outcomes. So there are 16 outcomes. 16 outcomes. They all have the same chance of occurring. So what do I have now? So we got four heads at the top. All right, so it's we're looking for how many of these outcomes have no heads. So let's look through this list and go. The only one that has no heads is that one. Okay, so there's only one of them with no heads. So that's 1 probability of the number of heads being 0. X is the number of heads. X is equal to the number of heads. And the probability of X being 0 is, what is it out of? It's out of 16, so it's 1 out of 16. 1 out of 16 is the probability of oh, Bob Green, hello. How do you block people again? I'm not used to doing this. So yeah. Now probability of X being 0 is equal to 16, 1 out of 16. And now let's go probability of X being 1. Alright, how many of these results have 1 head? Yes, we do, Panda. Isn't it funny? This is a math stream. Okay, you think that, you know, people here would, I don't know, be a bit more, what's the word? Would have civilized manners. Okay, so X equals 1. How many of these have 1 head? Should we count it? That has 4 heads, so definitely not that. I can see boom, boom, boom. This has 1 head. What else? This also has 1 head. And this is 1 head. Can you see any more with just 1 head? It's a bit hard to see. THTT, this also just has one head. So yeah, I can see 4 of them. No audio. Are you serious? Why don't you have audio? Can anyone else hear audio, or am I talking to myself? Is your sound on, Panda? Oh. So the probability of x being equal to 1, that's how many of these have one head, and I can see 4 of them, so the answer is going to be 4 out of 16. So 4 out of 16, let's write that here. 4 out of 16, we've covered that one. Now, let's see what else is there. Probability of x being 2. Probability of x being 2. Oh, thirsty. Everyone's gone. I must be really boring. Okay, so probability of x being 2 would be, you look through these and you would see how many of them have 2 heads. So that one's got 2 heads. That one's got 2 heads. Oh, let's use a different colored pen. A problem on my side. What? Can you hear audio when you play other videos on YouTube? Dun, 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 dun. Okay, well, I guess I'll keep going. So the chance of getting 2 heads So you go through this and you see how many of them have two heads. So you go 1, 2, 3, 4, 5, 6. 6 of them have two heads. Did I count that right? By the way, this is the slowest possible way of doing it. I'm just pretty much doing this to show you how slow it can be. So yeah, let's do another one. Let's do probability of getting 3 heads. So then you go 3 heads, you got 1, 2, 3, 4. 4 of them have 3 heads. And how many have 4 heads? You can hear audio when you play other videos. Okay then. Well, guess I've been talking to myself. Audio. Sound. Audio. Hello. Hello. Settings. Hello. Check your stream, see if audio is muted. I can hear it fine on my end. Okay, so what I'm going to do now is probability of x being 4. I have a feeling I might have, oh no I haven't. Probability of x being 4 is 1 out of 16, alright, because there's only obviously 1 tick left. So probability of x being 4 is 1 out of 16. Probability of x being 3 is 4 out of 16. And probability of x being 2 is 6 out of 16. Now, what do we notice about these numbers? What do we notice about them? So let's try adding them together. Okay, so we got 1 out of 16 plus 4 out of 16 plus 6 out of 16 plus 4 out of 16 plus 1 out of 16. And they all add up to 1. Okay, because 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus 1 is 16. So 16 out of 16. So that is equal to 1. Now, this satisfies what we call a discrete probability distribution. Discrete probability distribution, and that says that the sum, so that this term here means sum, the sum of all the probabilities of X occurring is equal to 1. Okay, and each probability is between 0 and 1. So you can see that these numbers satisfy both conditions. Each of these numbers is between 0 and 1, and they all add up together to 1. So the problem is it's taken a very long time for me to get these numbers. Isn't it? Takes me super long. So how would I get these numbers really quick? Okay, for example, if I change a number, if we change X to number of tails, will this be the same? Will these numbers be the same? And let's say I run an experiment for 6 times. Do I need to draw 6 layers of trees in order to get these numbers? So that's probably going to be too long. So we're going to think of a slightly better way. We're going to think of a slightly better way to do it. And the way that we're going to do it is called binomial distribution. And I don't know what's happening, so unfortunately I'm going to have to leave the stream. No worries, Panda. If you hover your mouse over the video, there should be a sound icon on the bottom left. See if it has been muted. And try turning up the sound. Click the sound icon to unmute. Binomial distribution. So what is binomial distribution? The binomial distribution is when there are only 2 possible outcomes for each trial. Okay, either you succeed or you fail. Now that sounds mean, doesn't it? Success or failure. Who wants to fail? But that's just the words that we use. Okay, either true or false, success or failure. Yeah, don't read too much into it. It's just option A or B. The two possible options, true or false. So what are some examples? What are some examples of that? Shooting a basketball, for example. Okay, here's a hoop. Basketball hoop. Probably need a backboard as well. Oh, that's a really bad drawing. But yeah, you're shooting a ball at the hoop. Shoot a ball and the ball is traveling. Does it go in? Does the ball go in or does it bounce out? You don't know if it's going in or out. Success or failure. Now we have two different probabilities. P we're going to call probability of success. Q which is the probability of failure. Now if you have a look at our coin toss example, this is exactly the same as binomial distribution because one watching. Yes, that's right. Nobody likes maths today. Because what was I going to say? Yeah, probability of success is 0.5 and probability of failure is 0.5 as well in the binomial distribution. Okay, that's cool. Well, where are you from? Punane Poker. It's a cool name. So yeah, what am I doing right now? Binomial distribution, probably a success, probably a failure. And we're going to also define n as number of trials. Finland. Oh, okay. Well, how old are you? So n is the number of trials, and in the binomial distribution, okay, there's basically some sort of formula, isn't it? Now, if you have a look at, for example, let's say we want probability of x being 2 in our previous example. Right? X means, for the people that have just joined in, X means the number of heads obtained from 4 coin tosses. And the probability, P is the probability. So if you toss your coin 4 times, what is the chance of getting 2 heads? Punang, do you know the answer to that? Before I go on, I just want to see if you know how to do it already. Okay, I guess you're not watching anymore. So from the probability tree, um, you can see that if I want to get the probability of one of these, the probability of one of these is 1 out of 16. Okay, now where does this number come from? Okay, the number comes from, if you start from the beginning, okay, you start from this point here and you toss your first coin. The probability of getting a head is 0.5. Now, if you toss another coin and the probability of you getting the head again is 0.5 again. So if you go 0.5 times 0.5, the multiplication principle, that tells you the probability of getting 2 heads in a row. So if you want to get 4 heads in a row, that's going to be 0.5 times 0.5 times 0.5 times 0.5. Okay, so that's going to be probability of getting 4 heads is 0.5 times 0.5 times 0.5 times 0.5. Right, because originally you had 50% chance of getting a coin head. After that, okay, let's say you're lucky enough to get a head after that. To get a head again, there's only half chance of getting another head. So half times half, so now you're on 0.25. So if you go 0.5 to the power of 4, let's bring up my awesome calculator. Where is my calculator? Can't find my calculator. So if we type into the calculator 0.5 to the power of 4, and we get 0.0625. So 0.0625. Okay, now you might say, well, the probability of getting 2 heads is going to be the same. Okay, because if you think about it, if you go probability of getting 2 heads and 2 tails, it's going to be 0.5 times 0.5 times 0.5 times 0.5 again. So it's going to be 0.5 to the power of 4 again. So it's going to be 0.0625 again. So isn't that easy? Isn't that easy, Pune? Or is there a problem with this? Or am I just talking to myself? So what I'm saying is, unfortunately, this is not that easy because the two heads might not occur at the beginning. Okay, there are many possible combinations where the two heads might occur. It might be at the beginning, or they could occur with a tail in between, or they could occur with two tails in between, or it could occur with two tails at the front, or it could occur with, right? You don't know how many combinations are there. So that's why we drew the tree. We drew the tree to see how many of them have two heads, and it ended up being 6 of them. Now, what is a quicker way of getting these 6 combinations without drawing the tree? Okay, because once we, where is the last possibility? We got one head at the front and one head at the back. We've already got that. Okay, let's just see. 2 heads at the front. HT, HTTH, TTHH, THTH, THHT. That's it. 2 heads in the middle. So once we've got 6 combinations, then we can just go 6 times 0.0625. Okay, because there are 6 possibilities, 6 outcomes out of 16 outcomes. So 6 times 0.0625. And that tells me the answer is 0.375. So yeah, that is definitely the answer for getting, what is it? Getting 2 heads. But the problem is that is way too slow. Okay, we don't want to write out these possible combinations every time we want to do this problem. So for a quicker way to do it, I'm going to show you the Pascal's triangle. So Pascal's triangle looks a little bit like this. So you might be seeing a little pattern as to how I draw it. Basically, the outside is always a 1, and then each number comes from the 2 numbers above it. So 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then 1 on the outside again. Okay, so it just keeps going non-stop. But what's useful about this Pascal's triangle is that, firstly, let's label the rows. Okay, let's go row number 0, row number 1, row number 2, row number 3, row number 4, row number 5, row number 6. So yeah, basically the second number in the row tells you the row number, so you don't. I guess you didn't really need to write that out. But basically, the row number represents n. Okay, the row number represents n. So n, if you guys can remember, which I said previously, is the number of trials. So if we want to know what is the probability of the number of heads obtained from 4 trials, then you go down to the 4th row, which is over here. Okay, 1, 4, 6, 4, 1. Now, how is that similar to this box that we drew beforehand? 1, 4, 6, 4, 1. Okay, so the Pascal's triangle is a quick way, a much quicker way of getting that number. Much quicker way of getting that number. So by drawing the Pascal's triangle, the number in the Pascal's triangle, these numbers here, represent the number of successes. The number of outcomes with that number of successes. Let me just write that out. Number of outcomes with number of outcomes with X number of successes. Right, so we got X is 1, there will be one outcome. X is 4, there are 4 outcomes. X is 2. So 1, 4, 6, 4, 1. X is 1, 2, 3, 4, 5. So when X is 1, there will be number of outcomes. When X is 1, there's 1 outcome. When X is 2, there are 4 outcomes. When X is 3, there are 6 outcomes. Actually, I think I just did that wrong, because X should be 0, 1, 2, 3, 4. Because we only have 4 trials. Alright, so for it to have no success, there's 1 outcome with that. For it to have 4 successes, there's 1 outcome with that. And then for it to have 1 success, there's 4 outcomes with that. 2 successes, there's 6 outcomes. So once we find out this number, we can just go 6 times 0.0625. Okay, so isn't that easy? Now, there are a few more complications. Okay, and that is that the probability of success and the probability of failure might change. So far we've been working with 0.5, 0.5. What if we change it up to 0.6 for the probability of success and 0.4 for a probability of failure? Oof. Let me just go get a drink. Be back soon. Oh. Pune, are you still here? Or have I bored you to death? So what I'm going to do now is give you guys the question. So let's say we want to n is 4 trials again. P is probability of success is 0.6. Probability of failure is 0.4. So then if I want to know the probability of getting 3 successes when n is equal to 4. So what you would do is you would go probability of x is equal to 3, right? So that would be 4 possible outcomes. So you would go 4 times. Okay, now what do you do? Now, because there are 3 successes, you would have p to the power of 3, because you're going to go p times p times p, 0.6 times 0.6 times 0.6, and then you're going to times by q, aren't you? Right, so then it's 4 times p to the power of 3 times q to the power of 1. So then the answer is 4 times 0.6 to the power of 3 times 0.4 to the power of 1, and the answer is 0.0864. Right, so that is the probability of getting 3 successes when you have 4 tosses. Does that seem right? 3 successes from 4 tosses. 4 trials. So let's just see whether I did that right up here. Seems a bit low. Oh, I didn't times by 4, sorry. Times that by 4 and I will get 0.3456. Oh, what a cool number is that. 0.3456 is the probability of getting 3 successes when you run a trial for 4 times. Okay, so if I did it one more time, okay, with the binomial theorem, so let's cut and paste this binomial theorem because I don't really want to, with the Pascal's triangle, so I don't want to have to copy all that out again. So let's go to the top. Okay, so we got n is the number of trials. So let's say n is 5. Right, we shoot the basketball 5 times. P is the probability of success. Let's say my probability of success is 0.8. Okay, let's say I'm an NBA basketball player shooting free throws, probability of success 0.8. Probability of failure is 0.2. Alright, so n is 5, that would be over here. Okay, what is the probability of getting 4 successes out of 5? So you're going to go probability of getting 0, 1, 2, 3, 4. 4 successes. There's 5 combinations. So you're going to 5 times. Now there are 4 successes, so probability of success to the power of 4 times probability of failure to the power of 1. So 5 times probability of success 0.8 to the power of 4 times probability of failure 0.2 to the power of 1. So put that in your calculator. Times 0.2 to the power of 1. And your answer is 0.4096. Alright, that is the probability of getting 4 successes out of 5 trials when your probability of success is 0.8. Okay, now there is another problem, that is I don't want to have to write out the Pascal's triangle, because what would happen if I had a number of trial is 20, right? Well, number of trial is 30. I'm not going to write out a Pascal's triangle with 30 rows unless you're super keen on that Pascal's triangle. Is there anyone else watching right now? Because if no one's watching, I might take a break. Tired. Professor X. Professor X, who are you? Xavier. Hey Xavier, don't watch back. Because I did this lesson really badly. I'll make a better version tomorrow or something. But I believe this is what you're learning next term. So it will help. Okay, so the problem with okay, yes, I'm pretty sure. Yes, I'm sure. I was reading the textbook as I made up the lesson. Not very good. I'll do a better version tomorrow. Okay, so what is a better way than having to draw out the Pascal's triangle? Isaac Lurs. Who are you, Isaac? So to get the Pascal's triangle, let's look at the Pascal's triangle again. And what I want to introduce you guys to now is a function called NCR on your calculator. I want to introduce you guys to this function on your calculator that is really awesome. Okay, it's called NCR. So if I can remember how to get this thing working, where is it? Math, probability, NCR. Now this is basically the function you use to predict the number that comes up on your Pascal's triangle. So if you go NCR, okay, and basically let's say I want this number in my Pascal's triangle. This number 6. Let me use a different color to highlight that. Let's say I want this number. So that's row number 4, position number 2, 0, 1, 2, isn't it? So let's just try that. Okay, let's just go row number 4. Oh, so let's just go quit. Let's just go for NCR two and see what number it gives me. It should give me 6. Yes. Okay, so this function here basically tells you the corresponding number on your Pascal's triangle. So if I want to know, for example, row number 6, the third number, let's just go the fourth number, okay, because the first number is 0. So 0, 1, 2, 3, 4. The fourth number on the 6th row, so you just go 6, math, go right to probability, enter. Oh, what happened? You go 6, math, go right to probability, go down to NCR, enter, 6 NCR, 0, 1, 2, 3, 4, 4, and guess what you have? You have number 15. So using the calculator, we found a super quicker way to get the number we want on our Pascal's triangle. So that means that instead of drawing the tree diagram, I can simply use a formula for getting the answer for a binomial distribution. And the formula basically looks like this. For a binomial distribution, so Xavier, are you doing much in the holidays? It's probably gone already. For binomial probability distribution, so every trial in the experiment, there are only 2 possible outcomes, success or failure. That's what makes a binomial probability distribution. For a binomial probability distribution, the probability of getting X successes is equal to NCX times P to the power of X times Q to the power of N minus X. Just blow my nose. Have a bit of a hay fever. So if I want to do, for example, the probability of getting, let's say, 6 successes out of 10 experiments, 10 trials, where the number of, so X is 6 times P to the power of 6 times Q to the power of N minus X, or 10 minus X, or 10 minus 6, which is 4. So what's P and Q? Well, then I can decide. Let's say the question says that the probability of success is 0.7 and the probability of failure is 0.3. Probability of success is 0.7, probability of failure is 0.3. Remember, these two have to add up to 1. Okay, because from each trial you either pass or you fail, don't you? You can't have anything in between. So let's put these in the calculator and see what it gives us. So then you go 10 C, so math, probability, NCR, 6 times 0.7 to the power of 6 times 0.3 to the power of 4. And what does that give you? 0.2. Okay, so that is basically the binomial distribution. So let's do a question and see if we can get it correct. Let's do a question out of the Maths Quest textbook. So let's go. It is known. Type out the question. It is known make the font a bit bigger. It is known that 5 out of every 8 people eat super flakes for breakfast. Find the probability that half of a random sample of 20 people surveyed eats superflex. Okay, so that shouldn't be too hard. Who is watching? Who wants to get this done before I reveal the answer? Xavier, are you still here? Professor X, are you still here? Don't have a book out. That's alright. I'll just show you how to do it. So you have probability of X having a certain number of successes. The question says half of a random sample of 10 people. So what's that? We want 10 successes out of 20. Alright, out of 20 people, we want 10 people to eat superflakes. So then we got NCX, P to the power of X, Q to the power of N minus X. So that is 20C10, P to the power of 10, Q to the power of 20 minus 10, which is 10 again. Okay, so what's P? P is the probability of success, and it says 5 out of 8 people eat superflakes. So probability is 5 out of 8 for success. Failure is 3 out of 8. So it's 20C10, 5 over 8 to the power of 10, and 3 over 8 to the power of 10. Let's put that in our calculator. So putting that in our calculator, we then have 20 math probability NCR 20C10 times 5 out of 8 to the power of 10 times 3 out of 8 to the power of 10. And what do we have? 0.0924. Okay, so let's see whether I have this correct from my Maths Quest textbook. 3-1, what exercise is that? 9C question 11. Yes, 0.0924, exactly correct. Oh, well, I guess this concludes our lesson on Binomial Theorem. Pretty tired today, so I might leave it here. Professor X, did you want me to keep going, or you wanna head off? If you want me to keep going, I can probably do a little bit more. Okay then, Xavier, thanks for coming today, being my only student. It's pretty good though, teaching something that is useful to someone. Oh, thanks man, appreciate it. Alright, well, I'll see you next time, Xavier.